Welcome everyone to the second part of this workshop. So now we're going to do the UM-Bridge tutorial component. I'm Reinarz, I'm at the Department of Computer Science in Durham University. And Linus, who also did the introduction part, is joining me in order to demonstrate how everything works. So what we're going to cover today is basically the entire process from start to end of how to use UM-Bridge. So we're working through an existing tutorial here, and that tutorial is also available online in our documentation. So if you go on UM-Bridge benchmarks.read the docs, then you can find this in the tutorial tab. You can also use this QR code to go directly there. And feel free to just follow along as we're going. So most of these things are designed to just run very simply. And you can immediately see if this is all working on your system. While Linus will also demonstrate to you what it should be looking like. Okay, so there's 6 sections to the tutorial. In part 1, we'll discuss how you interact with the existing UM-Bridge model. Then we'll discuss slightly more complex models. So if you've got a containerized simulation model, how do we work with that? That's part 2. And then we'll move on to the interesting stuff, or at least probably for this audience, which is how do we solve UQ problems on those models. And then we'll discuss what to do if you want to insert your own model instead of using one of our pre-existing ones, how to build a custom model container if you need that for your own model. And finally, we'll also discuss how to scale this up either on a cloud cluster or on any other kind of a cluster that you may have access to, so that you can get the most out of your models. So the first part that I want to discuss is how do we actually interact with the UM-Bridge model. So for this, we should just recall very briefly what a UM-Bridge model is. And that is, at least mathematically, just a function which maps some input parameter vector onto a model output. And in the software sense, what this is, at least in Python, is a class which supports certain things, all of them optional: evaluation, gradient evaluation, Jacobian action, and Hessian actions. And so then you can implement any or all of these for your existing model and then call them. So in addition to Python, which is largely what we'll be showing here because it's probably largely what you're interested in, we also support various other languages and frameworks. So for example, you could try calling the same model from some of our other supported languages, such as C++, MATLAB, R, or Julia. But for now, let's move on to just demonstrating how easy and straightforward this is. So we'll start with the first part of the tutorial and just briefly have a look what that looks like.
All right, so first of all, this tutorial requires Python and Docker for later steps where we want to run some existing models. In order to install Umbridge support for Python, that's just a package you can get through pip. And in my case, that's already on the system, so that was a fairly fast installation. The first step of the tutorial is about connecting to a UM-Bridge model. So let's try this out. The most basic thing you can do in Python for Umbridge is to essentially copy in these steps that we have over here, these 3 lines. And we can now go ahead and run the thing. So what is that doing? First of all, we are importing the Umbridge package. Next, we are setting up an instance of an HTTP model. This is essentially the client side of Umbridge. So this allows us to request evaluations of the function that our model provides, or to request gradient evaluations, Jacobian actions, Hessian actions. In order to do that, we need to point Umbridge to where that model is running. And in this case, we are taking a model that is running remotely on my own private server that we can use for testing. You can use the exact same 3 lines on your system, and it's going to also connect to my server and give that a try. So we're in addition specifying that we want to connect to a model named forward. Technically, that server could provide multiple different models, but in this case, it's just that one. Requesting an evaluation is then really just a Python call of that object. So we've just set up this model object pointing to where the model is running, and now we can pass in a parameter vector. In this case, we're just passing in a one-dimensional list with the value 11, and running the client, you see that the return value to that function is 22. And at this point, I can reveal to you that the model running on my server actually just multiplies whatever you throw at it by 2. So that's as expected. And we can now try, for example, passing in a different input value. And we get the expected output. In addition, the tutorial explains how you can get some further information about the model. For example, we could ask the model for whether it supports a gradient evaluation or whether it supports a Hessian action. So let's save that again and run. And we find out that this model supports neither gradient nor Hessian actions. All right. In a next step, the main point about Umbridge is that we get a high degree of abstraction, right? So what I've been using so far is a Python client to connect to that remote server. Alternatively, we can use a client that's written in C++ and point it to the same address. Oops. All right, yeah. We can run an alternative C++ client that behaves exactly like the Python client that we had a look at. I'm pointing it to the same address, and what we get is the same output, unsurprisingly, where it's multiplying my input by 2. Let's have a quick look at what this client looks like. So as kind of expected, C++ is a bit more verbose than Python, but in the end, what we are doing is again setting up an Umbridge client, pointing it to wherever that model is running. We're defining an input vector, in this case, just a single 1D vector with the value 100. And we are querying an evaluation from that model. Now, what's interesting is that this remote model is written in some programming language using some dependencies, but we have now successfully connected to it from both a Python client and a C++ client without changing anything about the model or without any specific adaptations to our clients making those evaluation requests. All right, so that's the basics of interacting with an Umbridge model in general.
Okay, so next maybe what we want to do is to be able to run that on our own system and not rely on your test server actually always being online. So perhaps we can have a look at running the same example just on your own machine.
All right, so to that end, in the Umbridge repository, we have a folder models, and you find a folder called test model Python inside. So let's just run this minimal model on my system now. And for example, I can take the C++ client that we just had. And now I'm pointing it to localhost, meaning my own machine, instead of my remote server. And what we get is, again, an output from that model that I'm now running on my own system. Again, just a single number. And it's going to, again, print out what kind of model names this supports and what the input and output dimensions are going to be. So as you see, nothing has changed with regards to the client that I've been running. However, I'm now just pointing it to a completely different model, in this case, running on my own system.
Yeah, and that's really the nice thing about this. So even though we communicate with HTTP, this does not imply in any way that you can only run UM-Bridge kind of externally somewhere. You can definitely run everything just on your own machine if that's what you want to be doing. Okay, so now let's already have a brief look at uncertainty quantification, and we'll have a more detailed look at that later, but maybe we can already try to run some UQ on this very, very basic model.
All right, so a very basic example would be doing uncertainty propagation on that simple model. So uncertainty propagation, as we've mentioned it before, I think, is essentially we start from a distribution of some potentially high dimensional value. We want to apply our model to it, and in the end we might compute something like the mean that we get after applying the model f to it. So in this particular example, let me run a client, an Umbridge client that is based on QMCPy, which is a Python library for quasi-Monte Carlo. And we might now again point that to the model that's now running on my own system. And after some quick computations, what we get out is a solution of 2.05. That's the expected value that QMCPy has estimated using quasi-Monte Carlo. Does that make sense? Well, we can have a look at the QMCPy client code. This is now quite a bit different from the basic example that I've showed you before, where we only made a single request to an Umbridge model. This code is now mainly quasi-Monte Carlo code using QMCPy. So after some Python boilerplate, we are pointing Umbridge again to where the model is running. But then we mainly have QMCPy code that sets up a quasi-Monte Carlo method on a distribution. And specifically now, just to check the values make sense, in that case, we define a uniform distribution between 1 and 1.05. And I can reveal to you that this Umbridge model is actually multiplying by 2, so the expected value that we've just seen makes sense. Most importantly, again, this is mainly QMCPy code. The only thing that's different to a standard QMCPy application is that we are not defining the model inside this QMCPy code, but instead we give it an Umbridge client that points to a remote model which could be running on my laptop, which could be running on a server, which could be running on a cluster, and it does not matter what language that model is written in or what kind of dependencies it uses, etc.
Great. Okay, so for everyone who's following along, you can try this out yourself. You can also try to write your own Monte Carlo sampler, which is the next task, which we won't be demonstrating here, but feel free to give that a go and just play around with the problem a bit. And next we'll be discussing how to move on to a slightly more complex model than something which is just multiplying by 2. So probably you didn't come here because you wanted to have models available which are so simple. Okay, so for that, again, we need to kind of think a little bit about what UM-Bridge actually does. And that is it connects our UQ codes to our model codes via HTTP and the UM-Bridge protocol, essentially. And so now we can, of course, communicate directly with the model, but we can also place this model into a so-called container. So if you're not familiar with containers, don't worry about it. All you need to do in order to run these is to install Docker on your own system. And we'll also discuss a bit later a bit more about Docker itself. It doesn't have to be a Docker container. It can also be a different kind of a container. That's fine. The main thing is that if we have a very complex model, like the one we'll be showing you, which is a tsunami example, which is maybe written in a language that your UQ client is not written in, which may have very, very complex dependencies. It may even have dependencies which you don't want to install on your system. Perhaps it wants a different version of some compiler than the one that you like to use, or it has just very, very complicated steps needed in order to install it. That is very, very useful if we can put it in a container. And so now what we'll be doing is we'll be using some of the models from the UM-Bridge benchmarks library in order to show you some more complex examples. And all of those are available for you to use as well. And they're on Docker Hub so that you can just run them wherever you are. So basically what we will be doing is we'll be connecting to one of those models, the same as in the previous section, and then we'll be able to follow exactly the same steps with getting input and output sizes and so on. But we'll also be showing you some of the more complex configuration options that you have that you don't really need with the very basic model.
So let's have a look at section 2 then, which is about running existing containerized simulation models. So for this section, we are starting with a tsunami model that is containerized and published by us as part of the Umbridge benchmark library. In order to run this on your system, all that you need to have is, as Anna mentioned, Docker support on your system, and then you can copy over this command. Ignore that I'm using Podman instead of Docker, it's equivalent for our purposes. All right, so I've already downloaded this, or I've already run this command before, so the Tsunami container is already downloaded onto my system. If that's not the case, you have a download procedure that maybe takes 1 or 2 minutes, and afterwards you'll be at the exact same point that I'm at, where the container image is actually being spun up, and we now have a running container where the simulation code is waiting for requests from Umbridge clients. As Anna mentioned before, this is an example of a very complex code with a lot of dependencies. So the installation procedure for the UQ expert coming down to just downloading that image and running it on the system makes collaboration with simulation experts quite a lot easier. All right, so we've got that model running. Let's do something with it. We can, for example, go to the Python clients that we've already seen in the Umbridge repo. For example, we have a basic Umbridge client that just connects to a remote model like we did in the very minimal example from the beginning. It is going to print the input and output dimensions of that model. We define an input parameter, and then we evaluate the model for that parameter. So let's just run that. And again, we have to point this client to where the model is running. In this case, again, it's running on my own system. All right, so this client now tells us the model server provides a model named forward. It expects 2 values as an input and 4 as an output. And then when evaluating, I'm running into an error where Umbridge tells me that the model expects a 2-dimensional input, but I actually just gave it a 1-dimensional input. So let's go back into the client code again, change the input parameter to actually be 2-dimensional. So maybe something like this. And we'll now again proceed by passing this vector into the model and see what happens. So now you see that once I run the client, there's actually something going on in the container, which is now running the simulation code and doing the propagation of the tsunami. And in the end, it's going to give me some outputs. In this particular case, the model tells me the values of water height at a couple of buoys at the maximum elevation. The output is, of course, very model specific. We can, for example, have a look at the documentation of the Umbridge model and benchmark library and have a look at the tsunami model, where we essentially get a brief description of what the inputs and outputs are going to be, what the model supports, what config options it might support, and a bit of background on the math as well as a reference to a paper that gives you all the detail about how that model is defined. All right, so now we've successfully connected to a pretty advanced simulation code that we didn't even have to install, and we've been able to request evaluations. Just a quick note, you see that we actually did 2 evaluations here that give slightly different outputs, even though when we have a look at the client, it's actually using the same input parameter for 2 subsequent calls. What's different in the second call is that that one is actually also passing in additional config options. And most importantly, we changed the level config option that this model offers. So these config options, those are all model specific. In this case, a level means essentially discretization level of this tsunami wave propagation. So setting this to 1 means we get a slightly higher resolution or slightly better resolved mesh in that simulation, and we get a slightly more accurate output at the cost of slightly more computational effort. So this, just as a quick side note, can also be quite useful if you want to do, for example, multi-level UQ methods. So that's very much within the framework. All right. Also, a quick note, the tutorial shows you how to access output files and so on, but in the interest of time, we'll just skip over that.
Yes, and quite in general, these config options are really open, so different models will have completely different configuration options. It's just passed in whatever the ones are for the model that you're using. So if you have a look at the documentation that Linus showed for a different model, then you'll see that the configuration options will be completely different. It's not always level and VTK output, for example. Okay, so let's move on to the possibly more interesting bit. So now we want to solve some actual UQ problems, and we want to solve them on our complex models, such as this tsunami simulation that we've already shown. So for this, let's briefly recap kind of what kind of UQ problems we might be interested in looking at. So the first class are propagation problems. So if we have a known distribution of inputs, how likely are certain outputs given our forward model? And then we normally want to look at some quantity of interest. So this means that we have some input data, which is here called y. We feed this into our forward model, which might be the tsunami example, or it might be something else, which is f of y. So this, in Umbridge terms, is just a call to evaluate. And then we compute from that some distribution of our quantity of interest. And maybe we're interested in the expectation value, so what's the most likely outcome of our simulation. And the second class of problems that we look at with this code are Bayesian inverse problems. And in this case, we're not giving some input parameters to the forward model directly. Instead, we want to know, given certain observations, how likely are certain parameters. And therefore, again, what quantities of interest are likely. So what this means is that we start now, instead of starting from the left and kind of moving forward, we're going to start from the right with some observation. So this might be the outcome of our tsunami simulation. So for example, we may know exactly what the wave height was at the buoys that are mentioned previously. And this might be our data. And now we want to know, given that, what parameters led to these observations. And so we kind of, in theory at least, just apply an inverse model. So instead of applying the forward map, we apply F inverse to our observations, and then we could get, again, a distribution of the quantity of interest. But of course, in practice, this is not so easy. Indeed, most inverse problems, if I pose them the way I've posed them here, won't even be well posed. They won't have a unique solution. They may not have a solution at all. And so what we're interested in doing is solving these kinds of problems as Bayesian inverse problems, using libraries such as PyMC. So we'll have a look both at a propagation problem and at a inverse problem now.
All right, so now in section 3, we start with propagation. To that end, we get ourselves a propagation problem from the Umbridge benchmark library. And again, I'm just running the Docker command that is given by the benchmark. So let's have a look at what this benchmark is actually going to do. So this simulates the deflection of a beam under load, and we get to modify the stiffness of the beam in 3 distinct sections. So we have 3 inputs for the stiffness and 31 outputs for discretization of that beam. And nice enough, this one also provides gradients, Jacobians, Hessians, and so on. But what we are interested in right now is a propagation problem where we now say we want to sample from a uniform, or we want the stiffness to be from a uniform distribution on the cube between 1 and 1.05 in each direction. We want to know the expected value of the deflection that comes out of it. So this is a depiction of some samples from that distribution and the corresponding deflections. What we want to see, for example, is now the expected value of the deflection at the end of the beam. So to that end, well, after launching this benchmark problem, which, by the way, is now implemented in C++ using the MIT UQ library, we're now going to apply QMCPy for sampling from that. Again, as you see, this QMCPy example client you find in Umbridge is already set up to sample from values between 1 and 1.05 in a uniform distribution. So just as we did before, we're going to run this QMCPy client. And we're going to point it to the address at which this model is now running. Now keep in mind, this is the exact same client we used before on the minimal server for some basic UQ. The only thing that has changed is now the model on the other side. So there was no specific change we had to make to the client in order to connect to now a very different model, which instead of a simple Python script is now a C++ implementation of that beam deflection. All right, so what's the output that QMCPy gives us? The solution output from QMCPy, that's the mean. As the last value we get, that's 971. So when we look at this graph, so roughly the mean should be around here. So 971 is pretty much in line what we expect from looking at that figure here. All right, so now we've performed uncertainty propagation using a quasi-Monte Carlo method implemented using QMCPy in Python on a simulation code in C++, which we didn't actually install on our system, but which we just grabbed from the Umbridge benchmark library, therefore giving us the simulation code as a ready-to-run black box, basically. Much more convenient than installing the MIT UQ library in order to set up your model first and then hooking this up to your Python codes.
Yeah, that's pretty cool. Can you maybe comment briefly on the ports that you're using for this?
Oh yeah, just a quick note. By convention, and it's maybe a bit even of a relic right now, a lot of our benchmarks actually run at port 4243 instead of the 4242, which we usually use. But ultimately, all that you need to do is point your client to the appropriate port and the appropriate address, and everything behaves exactly as expected.
Yes, exactly. So that's always the nice thing. So wherever your model's running, you just need to know where it is. Okay, so I think with that we can move on to Bayesian inverse problems. And here, because of the venue that we're in, we'll show you an example using PyMC.
All right, so for the Bayesian inference, the example benchmark that we are looking at is a Gaussian mixture, so a sum of three Gaussian distributions in 2D in that case. Again, we can run the model using Docker. This is also, again, part of the benchmark library. We're now going to use PyMC in order to sample from that distribution. So let's have a look at the PyMC client in the Umbridge repo. The PyMC client is, after a bit of boilerplate for, again, grabbing the console input or the CLI arguments that we pass in, the main part that we do is setting up an Umbridge op, and that's very PyMC specific. So we have a PyMC integration that provides an operation that fits in the framework of PyTensor, which PyMC is built on. So all that we need to do is define such an Umbridge op and again point it to where our model is running. From that point on, this op behaves exactly like any other operation in PyTensor and can be used as such, except that it doesn't implement the work itself, but it refers, or it basically defers that to a potentially remote Umbridge model, no matter how exactly that is implemented. All right, in the following, we set up QMCPy pretty much as, we set up PyMC pretty much as usual. We want to sample, so we define a density in PyMC to which we pass our Umbridge op that we've just defined. Then we instruct PyMC to find the map point, use that as a starting point, and afterwards sample from the density that the model provides and draw 100 samples. All right, so again, this is pretty much just normal PyMC code, except that instead of defining the model in PyMC, we refer the model to an Umbridge model that is going to be running wherever we like it to be, and that is going to be sort of accessible regardless of programming languages again. All right, so PyMC is going to be performing quite a bit of sampling there. And once that has completed, we're going to get a plot of the samples that we've drawn, which, I mean, it's not that many samples yet, but you can already recognize that these are basically 3 Gaussians added on top of each other, which we've just successfully sampled. Again, the same client could be now applied to any Umbridge model that provides a density to sample from, and that includes pretty much any inference benchmark that we have. I'm not going to demonstrate this here because a lot of the models that we have are considerably more computationally costly. So this will have to suffice as a quick demo, but you can continue from there.
Yeah, I mean, you can also try out the other analytic models we have if you want something that runs quickly, but not exactly the same example that Linus has shown, which is always the nice thing. Okay, so next, let's think about the next step, which is writing your own model. So if you're coming at this completely from an uncertainty quantification side, then maybe you think, oh, well, you've got tons of models available. That's great. I'm just going to use those. And that's great as well. But if you do have your own model and you want to use this, let's discuss a bit about how you get that in there. So essentially what you're always going to do is you're going to write your own UM-Bridge server, which defines your model. And I'm showing here some very, very minimal code for doing this in Python. But of course, you can do this in any other supported language that you like. And all that a very, very basic model would need would be it needs to know, well, the input sizes, so whatever parameter vector you're passing in, how large is that, the output sizes, and then it needs to implement one of the supported operations. So in this case, the example I'm showing only supports evaluate. It doesn't support gradients, Jacobians, or Hessians. But of course, you can write something which implements all, or in theory, also none of those. And then you can serve this model again as exactly as we've seen, even though this is a model you've written yourself. Nothing changes. You don't need to set up anything complicated. You can just run through the same steps that we've done. So let's have a quick look at what that looks like.
All right, so we'll continue with the minimal model that we've run before. So writing a server sounds a bit daunting sometimes to people, but in this case, Umbridge takes care of pretty much everything. So all that we need to do in order to define our model is to define the model class, define a name of the model, define input dimensions, output dimensions, and the actual operation that the model is supposed to perform. So in this case, you can see that this model is really just taking the first input, multiplying by 2, and returning it. So if you want to change it, let's say we want to multiply by 4. Okay, that could be much more complex things, but let's just try that for now. We can, again, just launch the server and connect our Umbridge client to that model. Now, again, it's complaining because my model expects a 1D input, but got a 2-dimensional one from the tsunami before. So let's just go into the client, change to a 1-dimensional input vector, and we're going to run the client again. So the only thing, again, I had to change in order to go to a different model was to make sure that I'm passing in the right input dimensions to my model. And as we expect, I've passed in a 100. I just changed the model to do a multiplication by 4. So this is really now using the updated model that I've just adapted. Going beyond that, you can now imagine, of course, doing much more complicated things than just multiplying by 4, but instead hooking this into your own, for example, PDE solver, simulation code, or whatever kind of model you want to implement. Maybe just to quickly show this again on this changed model now, again, we can also apply QMC Pi again, and we're going to get an expected value that is now taking our uniform distribution multiplied by 4 and then taking the mean of it. All right, so I think that concludes our quick look into how you write your own models. So we'll continue on with the next step.
Yeah, and I definitely recommend if you have your own model to just try this out, because I think you'll be surprised at how quick you can get your own model in there. Especially, of course, if it's just written in Python, you can just directly write it in there. Okay, so the next step is that we want to have a look at how to build custom model containers. So I already promised at the start that we'd have a bit of a closer look at Docker, and that's what we'll do now. So there's a large chunk of the tutorial which explains exactly how to do this, what you need to install. It explains all the different Docker commands as well. And we're not going to demonstrate this now, but if you're interested in it, then I'd encourage you to just work through that part 5 of the tutorial section yourself. So why should we be using Docker? Or indeed, why should we be using containerization? Well, the first advantage of it is that we can now install very easily. So this is exactly what we've seen. So actually this tsunami model that we've shown, which you can install just by running this very basic Docker command with the Docker run, is actually something that normally takes well, probably hours to install, and I've also had students who wanted to use this software who've actually taken days to install it. And this is because it's got a lot of external dependencies. It requires very particular compilers, and if you've got a slightly different system set up, then sometimes those don't work, and one needs to work out what versions of each of the many, many dependencies you need. And so by using a Docker container around everything, we completely circumvent this. And installing it comes down to a single command, which is very, very easy. Next is that it's system independent. So this means that you can give this Docker container to someone who's running Mac OS, you can give it to someone running some Linux version, or someone running Windows, and they can all run this. Versus a lot of, especially academic software, runs only on particular operating systems. Whatever the person who's written it happens to use is normally what it runs on. And this way, you avoid having these kinds of dependencies. And finally, for us, it's very important that we can also access high-performance computing resources, so HPC. So this might mean some small local cluster you have. Maybe you have a very powerful desktop computer which has many, many cores that you want to use, or maybe you have access to a supercomputer or to a cloud computing facility. And in all of those cases, we want to have easy access to this. And that means in particular that we don't want to have to muck around with how to install all of the many models that we provide on that system. And so in the last section of this, we'll discuss a bit more about scaling up and about using these kinds of environments and running models on them. I'll note now already that we do provide a lot of reference configurations for this, so that most of these things are made quite easy for the user. If you're interested in using Docker yourself, then they provide extremely good how-tos on this. So on the Docker page itself, you'll find their documentation, which explains how to install it on various different operating systems. It also gives you extensive documentation about how to get started, as well as class documentation. It basically has anything you can think of. And finally, I find the tutorials at Dive into Docker quite useful, which kind of walk you through the steps. But again, the other thing that we have is our own tutorial, which only walks you through Docker in the context of Umbridge, of course, but if that's what you're interested in using it for, then that's probably a good place to start. Okay, so in the context of Umbridge, the workflow is very, very simple. If we want to have a containerized model, we first need to start by creating a container image with our application, of course. And then we need to create the corresponding UM-Bridge server. So you already saw in the previous section that those servers are not complicated to write at all. What you want to give them is input and output sizes, and then you want to define how to evaluate and how to compute gradients and so on, if that's something that you want. So you need to create one of those for your application and then also place that into your Docker container. And now we can just run this. Again, we need to specify ports. And then when we call it, of course, we need to use the same port that we've used. So we have some conventional numbers that we always use, which makes this a bit easier to remember. But of course, you're free to use any unused port on your system. And now you can request model evaluations from your container image the same way as we've been doing. If you need to tweak the model, you update your Docker file and you rebuild it. So that's an important step, is that you also rebuild. And finally, if this is something that you think other people might find useful, then I definitely encourage you to also make it publicly available. And all of the benchmarks that are available in our benchmark library are also available on Docker Hub, which means that you can just run them out of the box by copying these commands, which are also in the documentation for each of those corresponding models. Okay, so for this section, we're not going to run you through creating the entire Docker container, because this is meant to be a workshop primarily on UM-Bridge. But if that's something that you want to do, then feel free to just work through this tutorial section. Okay, so the last part that we want to talk about is also quite exciting, I think, and that's how do we actually scale this up. So our goal is to make this as automatic as possible. So from our perspective, what we want to provide is something which is as user-friendly as possible. We want you to be able to use your Umbridge models for challenging problems, which often means that you need large amounts of compute resources. And this means that you're probably going to have to move to some form of high-performance computing facility. Whether that is in the cloud or a traditional system is irrelevant for that. And while we're doing that, we want to keep our UQ client simple, so you can just continue doing the same things that you've always done, just now with a lot more power behind it. So our wish list for this is, firstly, we want to avoid machine-specific model setup. So we don't want this to turn into something complicated where every single different type of machine needs its own setup, that all need to be written and maintained. And if someone has one that's not on the list, they can't use it. No, we want to have something which avoids that entirely. And then we want something which is parallel in both aspects. So we want, of course, to be able to run models which require parallel computing power. So for example, the tsunami model is one of those. If you switch that all the way up to level equals 2, that becomes very expensive, and you don't want to run that on a single core, you want to run that on multiple cores. So that's the first form of parallelism we want. And the second one is, of course, the one on the UQ side. If you're running a propagation problem, then these are generally embarrassingly parallel, which is to say you can generate a list of samples, and then you can run all of those in parallel, or rather you can run as many as you have cores, perhaps. Next, we want to have a single point of entry, so we want just the one UQ client which sends parallel requests. And finally, we want this all to scale well. We want automatic load balancing, so that our resources are being used as efficiently as possible. Okay, so if we're doing this in the cloud, we should discuss, at least very briefly, what that means. So if you have something which is shared memory parallel, you probably have no issues. But if you have something which is distributed memory parallel, for example, if you're using message passive interface MPI, then you need to think about it a little. So if you're using MPI within one container, this is completely trivial. You set up your container as usual, and you can then run. But that's restricted to one hardware node. So now you cannot communicate outside of that one node. If you want to get beyond that, then you can also do this, actually. So we provide a Kubernetes configuration for this. And in that case, you need to make sure that the model that you've set up, so if you've worked through section 5 to set up your own Docker container, you need to make sure that instead of starting from the standard Ubuntu base image, you start from an MPI operator base image. So let's have a brief look at what that might look like. Actually, we'll have a look at what it looks like in the most complicated possible setting, where you have everything switched on and all forms of parallelism that you could think of. So on the very left of this picture is your parallel UQ client. So this could be, for example, PyMC, which is going to send requests via the UM-Bridge protocol to our load balancer. And now there's a big box around everything else, and that's our Kubernetes cluster, where Kubernetes is orchestrating everything that's going on. And our load balancer is sending requests for model evaluations, which are coming from the parallel UQ client all the way over to our model. And now our model is again contained in a little box, which is labeled MPI operator. So now we've actually got multiple containers, which are the yellow boxes, all of which are running the same model together. And they don't communicate with UM-Bridge, they communicate via MPI now. In addition to that, we can also have an NFS server. So if you have large amounts of data that are required for your model, so whether this is, for example, in the tsunami example, this might be information about the height of the seafloor, so it's bathymetry data. But in other cases, it might be something else, then you can connect to an NFS server. If you don't have large amounts of data, if you only have your parameter inputs and outputs, you don't need to set this up. And we provide configurations for all of these things that you can just use. Okay, so I want to briefly mention what to do on a traditional cluster. So in this case, you often can't use exactly the same things. So if this is a cluster you administer yourself, then you can set up Kubernetes on this. You can just use these configurations that we provide. If this is a cluster someone else is administering and they're not letting you do this, you may need to do something slightly different. So in the cloud, what we do is what I've described on the previous slide. So we use Kubernetes to orchestrate our containers, and we use actually a modified version of their provided load balancer. And currently we provide two different configurations for that. So you can have parallel model instances with single node models, or you can have multi-node MPI parallel models. If you want to do the same thing on your HPC system, then it depends a lot on, well, firstly, what level of control do you have over that system? If you can install whatever you like, then you can go back to the left-hand side of the slide and use the cloud configuration, because you can just install everything you like. If it's an administered system, then very often they won't let you use Docker on that system. And so you'll be stuck with going somewhere else. What we often use is Aptainer, which was previously known as Singularity. But there may be other container systems that you want to use. And all of these should, in principle, work with your Umbridge. Although it will introduce a certain amount of overhead, and it might be a bit finicky to get MPI or things like that sorted with those containers. If your system has a queuing system, you also need to deal with that. And so we provide some example setups using Slurm, which is, I think, the most popular queuing system out there, that you can also just use out of the box. And there's still some ongoing work where we're trying to improve particularly the support for traditional HPC systems. So now Linus will again demonstrate how that looks like.
All right, so we're going to now assume that we have access to a Kubernetes cluster, but nothing has yet been installed on that cluster. Where you get access to that Kubernetes cluster is up to you. For example, we have a bit of an explanation of how you can do this with Google Kubernetes Engine, but likewise, you could also get this from some other public cloud systems, or you could install Kubernetes systems on your own machines. I have a running Kubernetes instance now on my laptop, so that's what I'm just going to use as a demonstration. So starting from that empty Kubernetes cluster, you can follow our Kubernetes instructions to obtain exactly that configuration that Anna just introduced, where you get a load balancer and you can spawn arbitrary numbers of Umbridge model containers. To get there, you can pretty much copy and paste the instructions that we have here. So first of all, we're using Helm, which is sort of a helper tool, in order to make this load balancer that we're using available on our system. And then we can apply a config file that we provide in the Umbridge repo in order to set up the load balancer. And that's it for that part. Next, the most important thing to set up is to use, of course, the model that we want to run. To that end, we have a model configuration file, model.yaml, where you can specify the Docker image that you want to run. You can specify how many instances you want to have running. In this case, I'm just using 12 because I'm running on my own laptop. On a large system, you could use hundreds or thousands. And you're going to specify what resources each model instance needs, how many CPU and CPU cores and how much RAM. We can now also just apply that configuration. And use get pods to wait until these containers come online. Now this Kubernetes system will have to download the container that I'm running here. And it'll take a second. By the way, the container that I've specified, that's this L2C model. This is also, again, part of the Umbridge benchmark library, so you can also run this for yourself. It's publicly available. Just to give you a brief idea, this is simulating a ship moving through water, and it's going to compute the resistance that this ship is going to encounter, depending on some inputs. All right, kube control get pods now tells us that all of our instances are running and ready. So finally, if you're running on a public cloud system, you might be able to access the addresses that your cluster is available at. In my case, I'm running on my own system, so I get direct access to what's running here. So these would be the IPs that you can use to connect to the cluster. The external IP could be, for example, available publicly, even if you want to make that happen. All right, so this is really all that you need in order to go from an empty Kubernetes cluster to a Kubernetes cluster with a load balancer and an arbitrary number of model instances, as Anna just previously introduced. So from this point on, we can actually start connecting to the cluster as we did connecting to a locally running model or a remote Umbridge model. In order to do something interesting, we have a client prepared in the tutorial directory of the Umbridge repo. And let's just have a quick look at this. So this is QMC Pi again for uncertainty propagation. There's a little bit of wrapper code in front, which essentially just fixes a large number of input values of this model. And the only input parameters that we change, I think, are related to the speed the ship is moving and the weight that it is loaded, if I remember correctly. So we're going to, again, instruct QMC Pi to sample from a uniform distribution on some 2D rectangle that we define here. And apart from that, it's pretty much exactly the same QMC Pi setup that we had used before. So again, notably, except for having a little wrapper that just fixes a lot of the model's input variables that we don't need here, this is really just plain QMC Pi. And again, we are not defining the model here. We're just pointing to a remote or to some Umbridge model that is running somewhere else. In this case, it happens to be also running on my laptop. One more important thing. Since we want to parallelize, we now are in the position where the load balancer is going to take care of distributing incoming requests from Umbridge across the running instances of our model that we have. So our UQ code is now allowed to make concurrent requests, and the cluster is going to handle them in parallel. So how do we get concurrent requests? In case of QMCPy, that's fairly straightforward. Essentially, you can just give QMCPy this parallel parameter, and it's going to do multiple of its evaluation requests simply concurrently using thread parallelism in Python. So let's run the thing by pointing it to the cluster. Again, this is running on my own system, so I can point it to localhost again. And now it's going to do quite a bunch of computations. We can see this by, for example, using htop, and you're going to see that now all these model instances are actually doing work. And you can see that my CPU is actually quite busy with running all of these simulation runs in parallel. Again, if this was a remote system where you might request thousands of processor cores from Google Kubernetes engine, you could really have hundreds of independent instances of your model running that each could be using dozens, hundreds, or even thousands of processor cores. We've tested it up to a couple of thousand processor cores, so and haven't really encountered scalability limits, so you can really go quite far with this setup. One more thing I'd like to mention, QMCPy is using thread parallelism here. This is really no problem running lots and lots of such threads on a laptop, because even if you're using sort of the computational horsepower of a remote cluster, the UQ algorithms tend to be relatively relatively computationally cheap, the UQ algorithms themselves, right? The computational effort comes from the simulation model. So it's enough to really just spawn maybe hundreds of threads on your own system that all pretend to be doing work while actually offloading it to a remote system. And to your UQ software, it just looks like you now have hundreds of models running on your laptop locally, and everything behaves as if that was actually the case. So that also means we can use different approaches of parallelism. For example, in the application mentioned in the intro with the tsunami and multi-level delayed acceptance, the UQ code that we've been using actually used Python's ray parallelization, but through Umbridge it comes down to the same. It's just the UQ code somehow produces concurrent requests, and the cluster takes care of distributing them across different instances, which makes this a lot easier to handle than if you had to interlink your UQ code's parallelism specifically with how exactly you handle instances running on a cluster. All right, so after about 90 seconds and running 12 models in parallel, we've generated 256 samples from that L2C model. And the answer we get is that in the mean, we get a water resistance of 73.47 encountered by the ship. And QMCPy gives us some upper and lower bounds and so on. So I have confirmed with the authors of the model that this is actually a sensible answer for the UQ problem that we are doing. So I count that as a success. And so that's just a basic rundown of how can you do parallel runs, scaling up existing UQ codes that were never really built for working with large clusters or something. And just imagine that instead of running that on my laptop, you can also use a Kubernetes cluster on Google Cloud with thousands of processors, and you get some serious horsepower behind that from your laptop even. All right, so I think that's it for the practical demo. So I'll hand over to Anna again.
Yeah, that's great. So as you can see, this is really straightforward to do, and you get a lot of scalability. So even if perhaps you're not yourself an HPC expert in any way, hopefully you can utilize the kind of compute power that we now have available. And as Linus has already said, there is a specific tutorial for Google Kubernetes engine, and I know that other people have used similar configurations also on AWS, so you're free to use the public cloud or your own cluster. In any case, that brings us to the end of this workshop. I really hope that if you haven't already been following along, that you do try this out yourself. And we'll be running a question and answer session as well, in which you can bring us any questions. If you view this after that's already passed and you run into any issues, then feel free to either contact us through the UM-Bridge Slack channel that we have, or just email either me or Linus. And we're really happy to to help with any issues that you may have run into. So thank you all for listening.